Hi everyone, I am Rajitha, working as an Assistant Professor of Artificial Intelligence and Data Science Department in SNS College of Technology. Today, we're going to see about mathematical analysis for regressive and non-regressive algorithm. Mathematical analysis of algorithms. Mathematical analysis of algorithm is the process of evaluating the efficiency of an algorithm. We mainly focus on time complexity and space complexity. So time complexity, how execution time grows with input size. Space complexity is how memory usage grow with input size. The key ideas is we study how the algorithm behave when the input size become very large. This analysis does not depend on machine speed, programming language, coding style. Instead, it depends only on the number of operations, the structure of the algorithm. This is why mathematical analysis consider accurate and universal. And a regressive algorithm. A regressive algorithm is an algorithm in which a function calls itself. Every regressive algorithm has two important parts: base case, regressive case. Base case is where the regression stops, and a regressive case where the function calls itself with the smaller input. Each regressive call reduces the problem size until the base cases reached. For example, of problems suitable for regression: factorial, Fibonacci, binary search, tree traversal. And regressive algorithms are often easy to understand because they closely match the problem definition. And recurrence relations. To analyze regressive algorithm, we use recurrence relations. The recurrence relation is a mathematical equation that describes the running time of a recursive algorithm. Common types: linear regression, divide and conquer. Uh, Linear regression, only one regressive call, example form T of n equal to T of n minus 1 plus C. Time complexity usually big O of n. Divide and conquer is problem divided into smaller sub-problems. Example form T of n equal to 2 T of n by 2 plus n, used in algorithm like merge sort. Then solving recurrence relations. There are three main methods to solve recurrent relations: substitution method, iteration method, and master theorem. Biggest substitution method is biggest the solution. Prove it using mathematical induction. Iteration method: expand the regression again and again. Identify the pattern formed. Master theorem, a direct formula method used mainly for divide and conquer algorithm. Using these methods, we finally express the result in asymptotic notations such as big O of n, big O of n log n, and big O of n square. This tells us how efficient the algorithm is. And non-regressive algorithm. Non-regressive algorithms are also called iterative algorithm. They use loops for while, no functions calling itself. Advantages: no regressive call stack, less memory usage, faster execution in most cases. Non-regressive algorithms are usually easier to analyze because we can directly count loop iteration. Analyzing non-regressive complexity and single loop runs n times. Time complexity is O of n. Nested loop, one loop inside another. Time complexity is O of n square. Dependent loops, loop bounds depend on each other. Uses triangular summation. This method is simpler compared to recursion relations because it does not involve functions call. Regressive versus non-regressive comparison. Space complexity. Regressive use stack memory O of n. Non-regressive constant memory of one. Code clarity, recursive, short and intuitive. Non-recursive, more control and clarity in execution. Performance, recursive, function call overhead. Non-recursive, faster execution. Choosing between them depends on problem types and resource constraint. And key takeaways, mathematical analysis help us understand true algorithm efficiency, and recursive algorithm are analyzed using recursive relations. Non-recursive algorithm are analyzed using loop counting and summation. Recursive solutions are elegant but may consume more memory. Non-recursive solutions are faster and memory efficient. This is the mind map for mathematical analysis of recursive and non-recursive. Thank you.